All right, everyone. So, um, again, a little bit late here, so sorry about that. We'll get started with the lecture for today. Um, you might have just noticed I am recording all of these lectures, and I'll put them up on Blackboard as well. So, if if something I said wasn't very clear to you the first time around, you can definitely go back and take a look for yourself again. Let's see. To come ready here. So all right. So, I guess a couple of things before we begin. Last time we went through the syllabus and all that, and somebody's already brought to my notice that you guys have a concrete exam on one of the dates, that we also have a quiz for mechanics. So I'll work with Professor Williams and see if we can find out a different day or a time that would work for you all. Uh, how many of you are enrolled in concrete as well? So you all have that conflict. All right. Um, and um, any other concerns about the syllabus and scheduling and logistics and stuff? No? All right. So very quickly, last time I was telling you about where structural mechanics fits into the context, uh, and what would be the focus of our study. Essentially, we'd be doing a lot of continuum solid mechanics first. So we want to learn how these types of problems can be solved. What are the meanings of these equations? How do we work with stress, strain in 3 dimensions, and so on? And in order to do that, we are going to have to develop some language, some mathematical language, which is basically also the first chapter in your textbooks. So we'll go ahead and begin with that. Um, so I think the first thing that I want to talk about is the difference between a mathematical description of physical quantities and the physical quantity itself. I mean, these are any physical quantity that you pick, a point. I have a few geometrical quantities here. Any physical quantity does not need uh, a coordinate system the way we normally are used to describing points in terms of coordinates and curves in terms of their set of points and so on. But there's a very fundamental difference between a physical abstract quantity, which we so for example, if I say define mass, um, it's an abstract quantity that's hard to define. We have to rely upon our physical understanding of these concepts to be able to do uh, uh, to be able to work with these quantities. So I'll go in two different ways here. One, in an abstract way, I'm defining what might be a point, a curve, a surface, a body, um, and we have to rely on our physical understanding of what these things are. And actually, if you open up a conventional mechanics book, there are pages and pages of descriptions of what a point is. What's the point? Right? Anyway, so what we also want to be able to do is to work with these quantities. So we have to find a way to mathematically describe them. Once we set up a coordinate system, and a coordinate system is not just three axes, x1, x2, x3, or xyz if you might be used to. It is defined by the location of the origin, O. Again, that location could be abstract. It could be the center of the earth, it could be the center of the sun, it could be the center of something. But to, to define this three unit vectors and the origin um, is basically how we are going to define a coordinate system. Once we define a coordinate system, in terms of that coordinate system, we can then find out what is the location of P. From the origin, we can measure the distance along E1, E2, and E3. And by the way, I am using these 1, 2, 3 numbers instead of X, Y, Z, which you might actually be more used to. And there's a very good reason for that, and you'll see that in a little bit. Because if you start writing in terms of X, Y, Z, sometimes your expressions are so long they'll go on for pages and pages, and you'll see that as well. So in order to avoid doing that, writing in terms of X, Y, Z, we're going to work with numbers, 1, 2, 3, and then we can use some operations on those numbers to write these expressions in a short form, which we'll get to. So anyway, the location of a point in 3 dimensions can be represented by this number, by these 3 numbers. But these 3 numbers aren't the point itself. That's a very subtle difference, a very minute difference, but an important one. Uh, the point itself is a physical quantity. It can be represented in terms of these 3 numbers with respect to a coordinate system that you define. The point is not the same as these numbers. I cannot write P is equal to x1, x2, x3. Okay, and this is a minor difference, but this will come up again and again, but it's an important difference. Similarly, for a curve, if you have a curve, the curve can be described in terms of a parameter, S. Here I've marked S. S is a parameter that's like a rubber length, if you will. You take that parameter S, it stretches from 0 to whatever value you want, and you kind of lay that rubber curve along this curve that you want to describe. So this curve C is a physical quantity that takes a parameter, a scalar parameter S, and it maps it. So this language is also important here. It maps it to points in 3-dimensional space where x1 coordinate is a function of S, x2 coordinate is a function of S, and x3 coordinate is a function of S. So that's how we describe a particular curve in 3 dimensions. And I'll come to a couple of examples on the handout in a little bit. Similarly, a surface is a 2-dimensional object, so it needs 2 scalar parameters, S and T. But again, the surface is a set of points where x1, x2, x3, it's the set of all of these points, and the locations of each of those points are given by those x1, x2, x3. But each of these coordinates are functions themselves of both the parameters S, T. S, T. And so, for example, if you pick a value of S and T as 0, 0, that picks out this point. Similarly, if you pick a value of S, T as 1 and 1, that picks out the opposite corner, and so on. So it's a continuous set of points that describes the surface. This is a way to mathematically describe this surface. And this might be bringing back visions of your calculus class. And indeed, that is exactly what this kind of description will be very useful for. I'll give you very, very, well, not very complicated, but reasonably complicated shapes to try to find the length of a curve, or try to find the surface area of a curved surface in 3 dimensions, which is bounded by these curves and so on. And in order to do all those kinds of things, generating these kinds of parameterizations of those physical quantities or those geometric objects is very important. And finally, for describing a body, we are going to obviously need 3 parameters. And yes, once again, all x1, x2, x3 will be a function of these 3 parameters R, S, and T. Here's a question. Let's say we go back to this curve here. Okay. So what does the value of S have to be between, say, 0 and 1? Or could it be between 0 and 10? Could it be between minus 10 and plus 10? Sorry? The value of S. So what I'm saying is, maybe I can take value of, when I described this curve, I said that the value of S goes from 0 to 1, okay? And then as the value of S goes from 0 to 1, my points trace out that curve. When the value of S is 0, I'm at A. When the value of S is half, I'm somewhere in the middle. When the value of S is 1, I reach point B. Does the value of S have to be between 0 and 1? That's my question. It doesn't have to be. It can be between any two real numbers. It's a rubber length. You stretch it as much as you want or shrink it as much as you want and just lay it around the curve. So indeed, it does not have to be between 0 and 1, and you can choose whatever is most convenient. So let's do a couple of examples here. The first one I'll do, and then the next one I'll ask you to do. To describe point P, in this case, for this body, I have these three coordinate directions defined here, x1, x2, x3. What are the coordinates of point P? How can I describe the coordinates of point P? What would be x1? X1 is in this direction. The point P is this blue dot that is one of the corners of this inclined surface. So what are the coordinates of this point P? We go A divided by 2. So this whole height is A. So A divided by 2 in the x1, A divided by 2 in the x2, and A, since this entire distance is 3A, this is A, so that's also A. So indeed, not very complicated. A is A over 2, A over 2, and A. Those are the coordinates of point P. Coordinates of point Q, similarly, are actually minus A over 2. And in x2, it would still be A over 2. And x3 would be 2A. Right, so that's a very simple description of the point. How would you define this curve, which is actually a line segment really, PQ? How would you define this curve PQ using a parameterization? Any ideas? You could do that. Yeah, you could do that. So here's one way to do that. We start from P and we need to go to Q. So what I'll do is I'll set up this parameter S, which starts from P, goes to Q, and as S goes from 0 to 1, I want my point locations to go between these 2 points. So in order to do that, I'm going to say that the curve PQ takes a parameter S and maps it to the set of points x1, x2, x3 of S, where the whole idea is what are these functions of S. So as S changes from P to Q between 0 and 1, the value of x1 goes from plus A over 2 to minus A over 2, right? So what would be a function that would allow me to do that? A over 2 minus S times A. Does that work? We can check. When S is 0, this term drops out. We have A over 2. That's the one, right? When S is 1, we get minus A over 2, which is this guy. Right? So x1, as S goes from 0 to 1, x1 goes from P. The x1 coordinate is mapped indeed from this point down to this point. So that's basically what we want in going from P to Q. And similarly, x2, what should be x2 as a function of S? A over 2, because x2 indeed does not change, right? In this this point is just A over 2. So x2 is not a function of S, or we can say that x2 is a constant function of S. So indeed, that's what this happens to be, and x3, a plus s times a plus s times a, right? And we also have to specify that the range that we took was between 0, s goes between 0 and 1. Now this is a mathematical description of that curve from P to Q. Okay. For a simple curve like this, if I asked you to, let's say, find the length of this curve, you could immediately use the Pythagorean theorem, a and a, and so square root 2a, end of the story. But if I give you a complicated curve where you have to find the length of that curve, unless you have a parameterization like this, you will have difficulty maybe finding the integral of the curve along that length. And we'll do lots and lots of those, well, not lots, but lots of those integrals to um, find out lengths and surface areas of objects before deformation and after deformation. Can anybody think of a reason why that might be important? Why would finding lengths and areas of things before and after deformation might be important? Exactly, that's what the definition of the strain depends upon. And a more concrete example is you have a reinforced concrete beam. When you have reinforcements in there, the initial length you know, after you apply the load it deforms and the length of those reinforcements change. And that will actually, how much they change is exactly how you'll find out the strains in those reinforcements and whether those reinforcements will yield or not, right? So it's to be able to do those kinds of problems, we need to be able to describe the objects more mathematically. All right, so how about this surface? How can I define this surface now? What would be the set of points that describe this surface? Say again? P and Q are just those two corners. Yeah, so I mean, again, I think you're going into the equation of the surface. Indeed, that is one way to do it. But in terms of generating a parameterization, we definitely need these two parameters. For a one-dimensional object like a curve, we need only one parameter S. For a two-dimensional object like a surface, we need two parameters. And okay, so we'll say S and T. And so the surface S is the physical object that takes these two parameters S and T and maps them to a set of points x1, x2, x3. Both are functions, all of them are functions of S and T. And it's our job now to define what those functions are. So for this entire surface, um, the value of x1, we can go from this edge all the way to this edge, and the same equation that we had for x1 here would describe the extent of this surface, right? So we can write a over 2 minus sa. So even though I'm writing x1 is a function of s and t, it's not really dependent upon t. As t varies, x1 does not depend upon t. T is actually perpendicular to x1. And similarly, x2 indeed depends upon t. What would that equation be? Okay, a over 2 minus ta. And indeed, we can check when t is 0, we get a over 2. When t is 1, we get minus a over 2. So that's indeed what we want. And finally, for x3, it will be as x3 again would not depend upon t because t is perpendicular to x3. So we would write that as again a plus sa. It would be the same equation. And in this case, we would have both s and t going between 0 and 1. Okay. Any doubts about any of these descriptions? So go ahead. Yeah. The value, so S and T are parameters. You pick. That's right. No, that condition is not given. That is entirely up to you. This is a S is a parameter. Maybe you don't like S, and maybe you want to use some other parameter, say U. Okay, so you could say that as U goes between -1 and +1, then what I would get is something that goes from -1 to +1 instead of S. If you use a different parameter, this range is entirely up to you. Maybe we should do that. Let's do that. I'll say let's pick a parameter U that goes between -1 to +1. Okay, and what I want is as my points go from P to Q, my value of S or my value of U should go from -1 to +1. Can I describe what x1 would be as a function of U? Maybe I'll actually define it here for the curve rather than this surface. So as an alternate, I could have written x1 as a function of U is equal to minus U over 2, sorry, minus A over 2. Sorry, so it would just be that's right, minus U times A over 2. So when U is -1, the value here is minus A over 2. Oh, sorry, plus A over 2. That's what this point is. When U is +1, I get minus A over 2. Does that make sense? So this parameterization, whether I use S or U or some other variable of your choice, and even the ranges of those numbers, 0 to 1 or -1 to 1 or whatever, is entirely up to you. Okay? The entire objective in this case is to try to define a parameterization that describes the point or the curve or the surface or the body. And there are infinitely many ways to do that. There is no unique answer to it. But we can easily check whether that parameterization works or not by plugging in those values of U and seeing whether the set of points that we want is traced or not. Okay? More questions? All right, so maybe you guys take a minute or two and see if you can do this next one. Parameterize the curve A to B. The curve A to B is this edge of this object that we looked at even last time. So how would you define a curve AB? So take a couple minutes, see if you can figure it out, and then we'll do it together. This is not a test, so you feel free to discuss with your next student sitting next to you, or even ask me a question if it's not clear. Let me give you a hint also. Um, oops. So hopefully you remember that if I have a circle like this, and if I have x1, x2 here, and if I want to map out um, a curve like this with, let's say, some radius a, then x1 as a function of a would be what? Oh, sorry, x1 as a function of, you create a parameter theta. So x1 as a function of theta would be equal to a uh, cosine theta. X2 as a function of theta is a sine theta, where theta goes between 0 and pi, right? So hopefully that hint should help you do this one. All right, I think maybe all of you got the idea of how you do it. It's the rest is more about details. But let's see. Following the same logic as before for this curve, I'm going to create a parameter this time, not s, but theta. So CAB would be a curve that takes the parameter theta and maps it to the set of points x1, x2, x3, all are a function of theta, and where x1 is defined as what? Sine, well, I guess, yeah, it depends upon, okay, so yeah, you can do that. So we'll write it as a sine theta, and where theta goes from minus pi over 2 to plus pi over 2. And we can easily check that, because when theta is minus pi over 2, uh, we get minus a, and indeed x is minus a at a. And when theta is pi over 2, so sine of pi over 2 would be 1, and we get x1 is a. So indeed it goes around like that. And similarly for x2, it would be x2 would be indeed a over 2, and x3 3a plus a cosine theta, right? So we are starting out at 3a, and so if you take this center point right here, starting from this point, when theta is minus pi over 2, we get 0, so that's this point. And as theta goes from minus pi over 2 to plus pi over 2, the values of x3 go from 0 to 1 and back to 0. Right, so you add that to 3a, and that would be the description of your, or the parameterization of this curve. Okay. Any questions about any of these parameterizations? Something not clear? Go ahead. X3. Okay, so what we want in X3 is that as I go from point A to B, I need to, the values of X3 should go from what? It should go from 3A to 4A at this point, correct? And then back down to 3A. And of course, as I go around this circle, the values increase from 3a to 4a, back down to 3a. And just like the hint, as I said, that would happen 3a here, 4a here, 3a here, and that's the component along the x2 axis. So um, in this case, when if I want to capture the point A at minus pi over 2, if I take the cosine of minus pi over 2 is 0. So I get 3a as I should. When theta is 0 in between, then I get 1, so that becomes 4a, and then finally 0, so it backs to 3a. Okay. All right. So let's keep going here. These were just geometrical objects, and in mechanics, we will often work with more physical quantities than just geometric objects. We'll of course work with scalars, vectors, and something, as I mentioned last time, tensors. We'll come to tensors maybe in a couple of next week probably. But scalars, as you well know, are physical quantities that are associated only with a magnitude, no direction. Right? Temperature is an example of a scalar. Density is an example of a scalar. Mass is an example of a scalar. Now, say that again. Yeah, there's lots and lots of examples of scalars. So in terms of notation, as we'll define scalars, would be these lowercase letters, A, B, C, or more often than not, these Greek letters. So when and actually I'm going to be extremely particular about notation. So since we are going to use this mathematical language to describe our things, if you even make a small mistake, like a comma where it shouldn't be or a dot where it shouldn't be, the whole meaning of the physical quantity changes. If you miss an underline on a vector, then I can't figure out whether you mean a vector or a scalar. So you have to be very precise with notation. Okay, so in terms of notation, we are going to denote scalars with these lowercase letters, and that's just scalars. But often in mechanics, we have to deal with fields, not just singular scalar quantities. For example, when I say temperature, is it meaningful to say what is the temperature of this bar? If the temperature of the entire bar is exactly the same, then maybe it's meaningful to say what is the temperature of this bar. But otherwise, in general, things or scalar quantities at different points of the bar in general will be different. If I have one end of the bar in freezing temperature, another end at the boiling temperature, there might be a gradation of temperatures from one end to the other. So we have to be very specific, saying temperature at a point. And similarly, later on you'll see velocity, for example, at a point, stress or strain at a point. So in general, these scalar quantities occur as fields. So what that means is that each point will have a different temperature, and we have to say temperature at what point are we talking about. So it's not, in general, it's not meaningful to say what is the temperature of this bar or what is the stress in this object. Stress in this object is meaningless. Stress is always at a point. Strain is always at a point. And of course, if we define a coordinate system, that means origin and 3 unit vectors. These 3 unit vectors are, again, maybe you're more familiar with I, J, and K, but we are going to use E1, E2, E3. And note again that even for these unit vectors, I'm defining E1 and with an underline. That underline denotes that E1 is a vector, okay? It's not a scalar. So similarly, if you want to define a scalar field, you have to define it in terms of what is the temperature at a point that is represented by the coordinates x1, x2, x3, or the density at a point, and so on. So indeed, most physical quantities of interest in mechanics would occur as fields. Okay. So and we'll work with all of those quantities as we go along. Similarly, vectors. Vectors, of course, as you know, are quantities that have both magnitude and direction. And here is where a most significant difference between an abstract physical quantity and its mathematical description will be is important. When I say that, let's say this object, um, if it's a rigid object and if it is not rotating, if it's going with some velocity, let's say a uniform velocity field over the entire object, then I can pick a point and say that the velocity of that point is this vector v. Okay, it's pointing, let's say, from one corner of this room to another corner of that of the room. So that's a physical quantity. It's a physical description. I do not need uh, I do not need a coordinate system to describe it. Okay, that's just a choice of just a convenience that we define a coordinate system to try to describe this vector. A vector is an abstract physical quantity that can be represented with its components in these three dimensions. So, for example, I could define this vector in terms of its components. I could say v1, the vector v is the scalar v1 in the direction e1 plus v2 in the direction e2 plus v3 in the direction e3. Okay, so that's a description of this vector in terms of these coordinate systems. In terms of this coordinate system, somebody else might come along and say, well, I don't like this coordinate system. I'm going to use a different coordinate system. Let's say this coordinate system: e1 prime, e2 prime, e3 prime, and all of them are underlined because they're unit vectors. In terms of this new coordinate system, I might get a different description of the same vector, which would be written as v1 prime in the direction e1 prime plus v2 prime in the direction e2 prime plus v3 prime in the direction e3 prime. Now it's important to realize that it's the same vector that we are talking about with reference to one coordinate system or a different coordinate system. And I should, of course, define an origin also. So origin together with the three unit vectors defines a coordinate system. So we will develop some shorthand notations for this also. As you will see, we don't really want to write this v1 e1 plus v2 e2 plus v3 e3 again and again. So a shorthand way of writing it would be, it is the sum of I going from 1 to 3 of vi ei, e is underlined again, which is also equal to I going from 1 to 3 of vi prime ei prime. Does that make sense? All I'm doing here is that saying that we need to sum over I. When I goes from 1, 2, and 3, that will generate term 1, term 2, and term 3. So we've taken a slightly long expression and written a shorthand notation for that expression. And this is the type of notation that we'll use again and again. Okay, and in this notation, what is a scalar? v1. v1 is a scalar, v2 is a scalar, v3 is a scalar. e1, e2, e3 are not scalars, they are vectors. When I multiply a scalar to a vector, I get a vector. Add one vector to another vector and to another vector, I get a vector. That's why I can write it as an equal to sign. V is equal to v1 e1 plus v2 e2 plus v3 e3. It's not represented by these three numbers. Now I know that quite a few of us use this notation from time to time, where we say v is, say, equal to v1, v2, v3. Is this correct? No, it's not, because this is not correct, because on the left hand side of this quote unquote equation, I have a vector, something that's a physical quantity, something that does not need a coordinate system to be defined. It's a physical quantity that has some magnitude and some direction. On the right hand side, I have three numbers. Those three numbers represent the coordinates, or the components, I should say, the components of that vector v with respect to a very specific coordinate system, but it's not equal to that. Okay. So what we can do to avoid this is we can say that v is represented by these three numbers. Represented, I'll write that as an arrow. So this arrow is okay. And to be more specific, I also should define that these three numbers with respect to 0, E1, E2, E3. But different three numbers, V1 prime, V2 prime, V3 prime, with respect to a different coordinate system, that would be O prime, E1 prime, E2 prime, E3 prime. Okay, so in general, it is important not only to write the components of a vector, but also to write which coordinate system is this referring to. Now that usually is not a problem, because for any given problem, you fix your coordinate system at the first. There is no other coordinate system. So it's understood that any three vectors, any three components that you write would be with reference to the coordinate system that you have defined. It's so generally we don't write this part, but if you have two or more coordinate systems floating around, it's important to write what are these components in reference to. Okay. Another thing, if I were to ask you to define what E1 is, well, how would you do that? What is E1? Say again. It is a unit vector, and indeed that is all we can say about it, because we can only say that E1 is a unit vector that starts from the origin O, which again is something that is abstract. It's some point in space, and it's pointing in this direction. That's all we can say about E1. We cannot use E1 to define itself, right? So in general, E1, E2, E3, the basis vectors of the coordinate system that we are using, and the origin itself, they are abstract physical quantities. But if I were to ask you to define the components of E1 with respect to E1, E2, E3, what would those be? What would be the components of E1? 1, 0, 0. So I would say that this is 1, 0, 0. And I'm going to omit this guy. I should define that this is with respect to this coordinate system, but I think that's understood now. So 0, 1, 0 would be E2, and E3 similarly would be 0, 0, 1. Okay. And note that I'm not saying that these are equal to that. They are, sometimes I use this arrow, or sometimes we use this tilde. But maybe just to be consistent, we'll use this tilde. I think later on in the course I've been using this tilde. So we'll say that the vector v can be represented with these three numbers, or these three numbers with respect to these different coordinate systems. Okay. All right, so looks like I've run out of my time here. Let's stop here, and then next time I'll introduce a more formal notation for this way of writing vectors, and later on scalars also, in this shorthand notation, which we call the initial notation. And this will have these indices I, J, K, lots of indices floating around. So you should maybe even try to read ahead, and we can have a more discussion in the class next time. All right, so see you all on Friday.